So, welcome back. What we are going to see in this video about conservation of energy, of mechanical energy, is that from the work done by the force, you will be able to find the potential energy, the U of X or U of Y. And what we will see also that from the net work refer to the work done for all the forces acting on the body. For the work done for all the forces acting on the body, they will produce a change in the kinetic energy. So these are the two basic equations. The work of one force, if it's a conservative force, is minus the change in the potential energy. Let's go to put it U, the change in the potential energy. And the other equation that we will use all the time will be that the net work, the work done for all the forces, the work done for the force 1, for the force 2, for the force 3, the three works, the three scalar quantities. Maybe this is positive, maybe this is positive, maybe this is negative. The total work, the sum, a number, is the change in the kinetic energy. Let's go to put it K. So here we put it K. Okay, so this is what we will see and what we will study. Now let's go to understand these things, this equation, the change in kinetic energy minus the change in the potential energy, in a way, or you see this equation also say that the change in the kinetic energy plus the change in the potential energy is zero. Or this equation say that the change in K plus U is zero. Or if the change is zero, it's because K plus U is constant. Oh, this is the principle of conservation of energy, that the mechanical energy defined as K plus U is constant. This is what we will work during the video. So to understand this principle, you imagine that you have two accounts. Let's say account 1, the potential energy, U. Account 2, the kinetic energy. Let's say that you are starting as in an initial condition where the kinetic energy is zero. There is no kinetic energy, then the object has velocity zero. If the kinetic energy is zero and K is 1/2 mv squared, so if K is 1/2 mv squared, this V is the amount of velocity, have no direction. V squared is the magnitude of the velocity. So if this is zero, it's not because the mass is zero, it's because the velocity is zero. Okay, let's say that we start with this situation. So we make a work, a positive work, and we put energy, kinetic energy on here. So when we do these things, when we do the work, the kinetic energy will increase, delta K. Let's say that we do a work of 200 joules. So what will happen? We place 200 joules of kinetic energy on the body. So now the body is moving with certain amount of velocity. What amount of velocity is? You put 200 here, 1/2, you put the mass, and you can solve for V squared to know 200 joules, how many meters per second will correspond. Of course, solving this will be 2 times K divided by M, square root will be the velocity V. So, when doing this, when you put 200 joules on the body, you increase the kinetic energy on 200, and you decrease the potential energy on 200 on the potential account, on the environment, on the field, on the potential energy of the field. So doing this kind of thing will make you that this equation will be valid. Delta K equal minus delta U. Why? because delta K increase in 200 joules minus delta U decrease in 200 joules. So it will be minus 200. So delta U will be minus 200. Delta K will be 200. So what it's saying is that 200 equal minus minus plus 200 is correct. So the equation that will take place will be that the change in the kinetic energy, it will be minus the change in the potential energy. You can do the game in the opposite side. For example, you have the object here. Let's say that the object have kinetic energy 800 joules. Okay, let's say that here is the potential energy. Let's say that the potential energy is 1000 joules of potential energy. So here is U, here is K. Now we can do the following thing. We can do work negative. Oh, now the work is negative. I'm extracting the energy of the body. Let's say that I'm extracting 200 joules. So the new energy, kinetic energy, will be 600 joules. This new kinetic energy will correspond to a new velocity. What velocity? Well, you know, because 1/2 mv squared is the kinetic energy. So, what happened with the potential energy? The potential energy now will increase to 1200 because I have taken the 200 joules from this object, it was, I taken 200, so now it's 600, and I place the 200 joules. 200 is flowing, 200 joules is flowing to the potential account energy, and so 1200 joules appear. So what is happening here is that the change in the kinetic energy is minus the change in the potential energy. What is the change in the kinetic energy? Well, from 800 to 600, there is a change in the kinetic energy of minus 200. Minus 200 equal minus, what is the change in the potential energy? Well, the change in the potential energy is from 1000 to 1200, there is a change, and the change is plus 200. Oh, it's true, minus 200 equal minus 200. So, it's correct. So if you work with these ideas, you will understand this equation, the change in kinetic energy equal minus the change in the potential energy. So we can transform kinetic energy into potential energy, back and forth. When the kinetic energy increases, the potential energy decreases. And we can do it forever if the force is a conservative force, if there is no friction in the middle. You can do it forever. So the total mechanical energy is defined by the sum. It's a number. It's a number. It's not a vector, it's a number, it's the sum of the kinetic energy. This is a number plus the potential energy. This is a number also. And this is the mechanical energy, E, at any point. So K depends on X. So we can put it K depends on the position, maybe, yes. And U depends on the position. But the sum will be constant if it's a conservative force. So this amount, the E, the mechanical energy, will be conserved. And that will mean that if K grow, U have to decrease because the sum have to be constant. If K decrease, is converting a number that is smaller, the U have to be bigger in order to the sum to be constant. So that's why the change in K is minus the change in U. Okay, so the mechanical energy is conserved if the force is conservative. There is a gain where the kinetic energy increase and the potential energy decrease. Or opposite, the kinetic energy decrease, so the velocity decrease, and the potential energy increase. Let's go now to see one example. Let's go to erase here. Let me erase here. Let me erase all these things. Let me erase all these things. And let's go to do one example. One easy example is a spring. The spring have a constant K. So I'm going to do one example. Example can be example. So you have a spring. Let's say that this is the equilibrium position. So you have a mass M. Let's say the mass is 2 kilograms. Let's say that the constant of the result, the force that the spring is doing on the mass, when you stretch, there is a force on the mass, and the force is in this direction. It's in the opposite direction at the displacement. The displacement, x or delta x, if you prefer, but I have chosen x equals 0 here. The displacement delta x is positive, but the force is negative. So the force that the spring is doing is minus kx in the I direction. So it means that if the x is positive, the force will be negative because k is positive. So the force is in this direction, in the negative direction, to stretch the spring. So the example is like this. I have a mass m of 2 kilograms. Let's say that the equilibrium position, the velocity is 30 meters per second. Okay. To this force, there is a potential energy associated, U, that depends on x, that is 1/2 kx squared. Okay, so the problem is, if, part A, if x equal 1 meter, what is the velocity of the object, of the mass? So the force is in the negative direction. I'm moving from A, from this position A, to the position V that is 1 meter ahead, 1 meter. So this is the position V. The mechanical energy is conserved. So how I will find the velocity V at this point? It will be smaller or it will be bigger? Well, the work done by the force is going in this direction, so the displacement is going in this direction, in the positive direction. The work is negative, so because the work is the change in the kinetic energy, it's clear that if this is negative, the change in the kinetic energy should be negative. So the velocity will be smaller. So let's say that the velocity, the initial velocity is 3 meters per second. What will be the velocity when this distance is 1 meter? So you will apply a principle of conservation of energy. You will say that the mechanical energy that exists at the beginning is conserved. And what is the mechanical energy that exists at the beginning? The mechanical energy that exists at the beginning is the kinetical energy initial plus the potential energy initial. What is the mechanical energy initial? The mechanical energy is 1/2 mv squared. This v squared initial is the 30 meters per second squared, plus u initial. U initial is k x initial x squared, But the elongation, the initial elongation, because he is at the equilibrium position when the v is 30 meters per second, the x is 0. So the mechanical energy in the initial state is 1/2 the mass, 2 kilograms, the velocity squared, 30 squared, plus 0. So the mechanical energy initial, it will be the 2 divided by 2, it will be 900 joules. So initially, I have 900 joules of energy to be conserved and to be shared between kinetic energy and potential energy. So what is the mechanical energy final? The mechanical energy final is the kinetic energy final, B final squared, plus the potential energy final, 1/2 K X final squared. Let's go to evaluate this quantity when the X final is 1 meter. So it will be 1/2, the mass it will be 2, the velocity is my unknown, is what I don't know, plus 1/2. This K is not the kinetic energy, it's the K of the spring. Okay, don't be confused with this K initial. This K is the constant of the spring. And the constant of the spring is 10. The final position is when x equal 1 meter, so it will be 1 square. So as a result, the mechanical energy final will be Vf squared, the 2 cancel with the 2, plus 10 divided by 2 plus 5. So the equation says that the mechanical energy is conserved. So the initial mechanical energy equal to the final mechanical energy is a quantity that is conserved. Initially, I have 900 joules. Finally, I have Vf squared plus 5. So what is the final velocity? The final velocity, Vf squared, is 900 minus 5. So the V final is the square root of 895. So it's almost like 30 meters per second, almost, a little bit less. Of course, because the work has been negative, so I have to lose some kinetic energy. So when he displays 1 meter, the velocity is like 29.5, I don't know, square root of 895, maybe 29.8 meters per second. So almost have not decreased his amount of velocity in 1 meter. The part B will say like this, part B. At what distance x from the origin, from the equilibrium position, the final velocity will be 0. So when the object stop for not for a second, stop, after that he will come back, because the force of the spring will pull the object to the equilibrium position. At what distance x? So the initial energy that we have is 900 joules. What is the final energy? The final energy is equal to the initial energy. So the final energy is the 900 joules. But what is the final energy? Is 1/2 mv final squared plus 1/2 k x final squared. This is the potential energy U final. So the final energy, the final mechanical energy is kinetic energy plus potential energy. So the equation will say 900 equal. What is the kinetic energy final? We want to go to the point, to the extreme point, when he has lost all the kinetic energy. So the kinetic energy will be 0. Equal 1/2 k, and what we want to find is the x final squared, the x final. The k is not the kinetic energy, the k is 10 newtons per meter. So we have this equation 900 equal 5 10 divided by 2 is 5 by x squared. So the x squared will be 900 divided by 5. So 900 divided by 5 is how much? 20, oh, how much is? Between 10 is 90, 180 meters. So x is a square root of 180, that is more or less 13.5 meters. So the object will stop for us, not for a second, for a millisecond at x equals 13.5 meters from the equilibrium position, from the position where the object is at equilibrium. So this is useful applications of conservation of energy. Let's go to more things. So complicated problems are solved easily using conservation of energy. For example, imagine this problem. This problem, the object is falling down. Let's say that there is no friction here. So the acceleration, this is the weight, applying Newton's law, the weight will be here. This will be the force in the direction of the displacement, mg sine of theta. It will be the force going in the direction of the displacement, and you know how to calculate, for example, what is the velocity here. We have done before applying Newton's law, but so you will say, what is the advantage of using this concept of work and energy? Well, the advantage is here. Imagine that the surface is not flat. So now the surface is not flat, is something like this. Imagine it's a ski mountain, and you want to find the velocity when the guy arrives here. Oh, now using Newton's law will be very difficult because the displacement and the force and the weight will go like this, and the displacement is going like this. So the acceleration is going in this direction. This is the acceleration, A, going in the direction of the displacement. But because the curve is changing all the time, the displacement will go like this now, and therefore it will be another acceleration. It will be changing the acceleration all the time because the weight will be like this, and the displacement now is in a different direction, delta S. So mg, the angle, will be changing. So the mg sine of theta will be changing the force. So it will be very complicated. But using conservation of energy, you will say, okay, what is the potential energy at the point A? At the initial point A, what is the kinetic energy? Well, the mechanical energy is potential mass plus kinetic. Let's say that the initial kinetic energy is 0. What is the mechanical energy at the point B? Let's say that this is the point V. Oh, it's potential energy plus kinetic energy. So let's say that is at the bottom, is when the H is 0, so the potential energy is 0. So what is the K? The equation will be very simple. The mechanical energy at this point A, at the initial point, will be mgh0 plus 0. So the total mechanical energy will be mgh0. The total mechanical energy at the point B will be kinetic plus potential. Kinetic, I don't know, 1/2 mv squared, mv by the velocity b at the point B square. Potential will be 0. So because the kinetic energy, because the mechanical energy at the point A is equal to the mechanical energy at the point V, I can conclude that the velocity v sub v squared will be 2 times gh0. The m will cancel, and the velocity v sub v squared is 2 times gh0. So one problem that could be difficult like this one is solved in an easy way using a conservation of energy. Okay, so to make a summary, the work is the change in the kinetic energy. The change in the kinetic energy is K final minus K initial. The work, this work is the work done by the net force, by all the forces, not only one. If there is only one, the net force corresponds to the work done by one force, if there is only one. So, if there is conservative force, the force comes from a potential energy, and we will find the potential energy right in this equation. The work equal minus the change in the kinetic energy, minus U final minus U initial, so this will be equal U initial minus U final. So if the work is this, and the work is the change in the kinetic energy, and the work is minus the change in the potential energy, the equation that I will have is that K final minus K initial equal minus U final minus U initial. So reordering this, I will have that K final plus K initial, K final plus potential energy initial final will be a K initial plus potential energy initial, or in other words, the mechanical energy initial at any points, at the initial points, equal the mechanical energy final. And this is the principle of conservation of energy. So if delta K is positive, delta U, this will be positive, so delta U will be negative, minus something positive. If delta K is negative, delta U, negative with negative is positive, delta U is positive. And of course, if delta K is 0, means that the work is 0, the net work is 0. What happened with delta U? Well, delta U will not change if there is only one force. So if delta K is 0, delta U is 0, so U will be constant. Wow. So please pay attention to this K when you, for example, here you start with one situation of certain amount of potential energy and certain amount of kinetic energy. There is a interchange here of energy. In this case, the U will give energy to the K account. So the kinetic energy will increase this amount, delta K, while the potential energy will decrease this amount. And the change in K is always minus the change in U. And this is the equation that will happen always. Here we have only one potential energy. We will see later on the case when we have two forces acting on the body. So we will have two U's here, two U's. We will see it. Okay, here we can see it. So imagine that you have this body. This is the spring. There is a force on the object due to the spring. There is a force. Let's say that this is the equilibrium position. If you go from position A to position V, what will happen here? If you go from position A to position V, on the object there are two forces acting. On the object there are the weight going downwards. And there is the force. If this is the equilibrium position, and you displace to this, you displace certain amount x or y. In this case, y. What will happen? That there is a force of the spring going up. So the force of the spring will go up. So the spring will make going from A to V downwards, here was A. In going from position A to position B, the weight will do a positive work, while the spring, the force of the spring, will do a negative work on the mass M. This is the object with mass M. The object has mass M. So this process of going from A to B is being solved by applying conservation of energy. What will say the conservation of energy? Will say the mechanical energy that exists at the position A is equal to the mechanical energy that exists at the position B. What is the mechanical energy that exists at the position A? At the position A, there is mgHa. This HA, potential energy. There is maybe elastic energy store, 1/2 kxa squared. There is maybe kinetic energy store, kinetic energy at the position A, 1/2 mva squared. So this is the total mechanical energy at the position A. Is kinetic energy plus 2 potential energy, gravitational potential energy and the elastic potential energy. So at the position A, this is the total amount of mechanical energy. So this is E mechanical. But E mechanical have to be conserved. So there is an interchange between the 2 potential energy here and here. Maybe this potential energy increase when the object is going to A to B, while this is decreasing because the H is being decreasing. The HB will be this amount, HB. Okay, so what we are going to write is an equation that says that the total mechanical energy at the position A equal the total mechanical energy at the position B. At the position B, there is potential gravitational energy, mgHb, this height. There is some elastic potential energy, 1/2 kxv squared. And maybe there is also kinetic energy, 1/2 mv squared. So using this equation, you can solve a problem where they say, for example, find the amount of elongation, not of compression or elongation at certain point. We will do some problem in the next. You will find a video that show you how the conservation of energy can be tested. So please see the video.
I have here a pendulum. I have an object that weighs 15 kilograms and I can lift it up 1 meter, which I have done now. That means I've done work. mgh is the work I have done, believe me. I've increased the potential energy of this object. 15 times 10, so 150 joules. If I let it fall, then that will be converted to kinetic energy. If I would let it swing from 1 meter height, and you would be there and it would hit you, you'd be dead. 150 joules is enough to kill you. They use these devices, it's called a wrecker ball. They use them to demolish buildings. You lift up a very heavy object, even heavier than this, and then you let it go, you swing it, thereby converting gravitational potential energy into kinetic energy, and that way you can demolish a building. You just let it hit, and it breaks a building. And that's the whole idea of wrecking. So you are using then the conversion of gravitational potential energy to kinetic energy. Now, I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0. Physics works, and I'm still alive. I have an object that weighs 15 kilograms.
Now I want to check these kind of problems. Let's say that you have a spring here. This is the spring. On the first step, you may do a force on the mass m in this direction. Maybe you do external force. This is not the force of the spring, so you compress the spring. Now you compress the spring and you store energy on the spring, a certain amount of energy on the spring. That is the work that you have done on the spring to store the energy. So we start the problem from here. There is some potential energy here at the point A. Let's go to call the point A, and this is the point B. And let's say that the problem asks you, what is the final H? Let's say that the initial H is H initial, and this is the H final. What is the final H that when, at what H will arrive the body of mass m? So how you will do it? Well, you will say, I have a problem of conservation of energy. The energy is conserved. The total energy that I have at the point A is the total mechanical energy that I have at the point A is the total mechanical energy that I have at the point B. So I will place an equation that will say U elastic 1/2 kx squared. Mechanical energy initial is kinetic energy initial, potential energy initial, gravitational energy initial. You know the expression for each term. The expression for the kinetic energy initial is 1/2 and V initial squared. The expression for the potential energy initial is potential energy elastic is 1/2 K x squared, the compression square. And the expression for the gravitational energy is mgh. So at the point A, there is this amount of energy is shared between kinetic and the two potential energy. Maybe K is 0 because the velocity is 0 at the point A. Maybe U is 0 because the object is at the floor. And maybe the U elastic is the compression of the spring and is certain amount of potential energy stored. So the mechanical energy initial will be only due to this term. The final mechanical energy is the same. is the K final plus the U due to the potential energy due to the elastic spring to the spring, and U the potential energy due to gravitation to the force mg. So each term has an expression equally like this. The U elastic is 1/2 kx squared. So in the case that you start with the position A with kinetic energy 0, what is the total energy? Is K0 is 0. There is only compression. 1/2 kx squared. And let's say that the kinetic energy is 0, so you will have 1/2 kx squared at the position A. What is the mechanical energy at B? At B, the total mechanical energy is only, at B at the maximum height, there is no kinetic energy also, there is only potential energy, and there is no, the spring have no compression. So the elastic potential energy is 0. So in the final state, E initial equally final, E initial is K initial, that is 0. So the only energy initial that I have is the potential energy, the elastic potential energy, 1/2 kx squared. And E final, at the maximum height, the only energy that I have, the only term of the mechanical energy that will contribute, U elastic will be 0, the K will be 0, so it's only mgh, the potential energy due to gravitation. So mgh, this will produce an equation that if you give me the compression, the x, and you give me the k, the constant of the spring, this is not the kinetic energy, sorry that this k is confused with this k0, this is kinetic energy, but this is the constant of the spring, the k newtons per meter. So this will allow me from this equation to solve for h. So you can imagine a problem and you can solve the problem for the maximum h will be kx squared divided by mg and the 2. This is the h. So what happened here in terms of conservation of energy? In the initial state, the total energy will be only elastic potential energy. The K will be 0, and the gravitational energy will be 0. At the point B, the final state, the K will be 0, the U elastic will be 0, and the U elastic that was at the initial state is converted into potential gravitational energy, so this will be the U gravitational. So this is the final state at the position V, this is the initial state at the position A. So the whole energy has been converted from elastic potential energy to gravitational potential energy. And in the middle of the path between A and V, the kinetic energy has increased a little bit. The elastic potential energy, maybe it has increased a little bit, and the potential energy maybe have increased a little bit, but the sum of all these terms will be this one, because the mechanical energy is conserved. So the K, the U elastic, the U gravitational. So the U gravitational, so after some times, the K will increase a little bit, the U elastic will decrease a little bit more, and the gravitational will increase a little more. And finally, you will arrive to this situation. So there is an interchange. I give you, you give me. I give you, give me, like the bank account. So potential energy always depends on positions. Always depend on position. So imagine that you have a roller coaster going in this going like this. You launch the roller coaster from here, maybe with certain velocity v. So the roller coaster will do like this. Meanwhile, he's doing like this. The potential energy depends on the h. So at every point h, the curve of the potential energy will be mgh. So mgh will mean that the shape of this roller coaster will be the same shape of the potential energy, because the potential energy is mgh. So at this point, this is the h. At this point, this is the h. So the potential energy is mgh, so it will be the same shape for the potential energy that the shape that is here. Okay, so now imagine that you place the object with this total energy, mechanical energy. So if you place the object here with this mechanical energy, the object will have this potential energy. So the mechanical energy, it will be potential energy plus kinetic energy, Q plus U. So in this case, if you have the object at here, and this is the total energy, the red line, this is the total energy, the red line, so it will say that there is no kinetic energy, because if the mechanical energy is all these amounts until the red line, the first red line, this, it will be K plus U, but U is mgh, so K will be 0. So at this position, with this mechanical energy, the potential energy, it will be mgha, but because the mechanical energy, the curve of the total mechanical energy is here, the kinetic energy should be 0. Now, if the total mechanical energy of the object is this one, the second horizontal line for the total energy is an horizontal line because it's conserved, it's always the same amount, never change. So if you have this total energy, let's say E2, let's say that this was E1, and you are here, you have this amount of potential energy and this amount of kinetic energy. And now the sum, it will be all this. The sum will be the mechanical energy. The mechanical energy is this kinetic energy plus, potential energy, mgh, plus kinetic energy. So at this point, the object will have kinetic energy if the total mechanical energy is E2. So the question is like this. If they have E2, can the object starting here arrive to here? And the answer is no. He will not be able, having mechanical energy E2, to arrive to this top of the point. Because as he moves, the potential energy decrease and the kinetic energy increase. Now, the potential energy increase, the kinetic energy decrease. Now, the potential energy increase, the kinetic energy decrease. Now, I'm talking about the curve that have energy E2. Now, the potential energy decrease, the kinetic energy increase. Decrease, potential increase. The increase, decrease. But it can arrive to here because at this point, all the energy at this point will be potential energy. So E will be equal to U. So there is K equals 0. So at this point, with this mechanical energy E2, the point will be with velocity 0 at here. So you start from here, and you can arrive to here. You cannot arrive to here because here, with this amount of energy E2, the kinetic energy will be negative, but the kinetic energy cannot be negative. So this is interpreting graph of potential energy. To interpret the graph of potential energy, you have to see this equation. The force, the work, the force Fx on the direction of the displacement by the displacement is minus the change in u. So the force on x is minus the change in u divided by the change in x. But what is the change in u divided by the change in x? Is the slope. The change in u, this is u, this is the change in u. In this case, is positive, the change in u from going from here to here. And the change in x is the slope. So the force is minus the slope. What it means this? It means that if the slope is positive, like in this case, the force is negative, going to the left. For example, in this part of the graph of the potential energy, the slope is negative. So the force is positive. So the force is going in this direction, positive, because the force is minus the slope of the graph u of x. Delta u divided by delta x is the slope of the graph. So the force is minus the slope. So when you are here, for example, the slope is positive. So the force is negative, going to this direction. So when you are here, the force, the slope is negative. So the force is positive. When you are here, the slope is positive. You see, the slope is positive, so the force is negative. And when you are here, the slope is 0. So the force is 0 here. Wow. So you can analyze, this is very important, this graph of u of x, to analyze the motion of objects. Okay, let's go another more concept that is power. Power is the amount of energy delivered divided by the time elapsed. You can deliver a big amount of energy in a small time, in a small elapsed time, so your power, the power will be very big. So the power multiplied by the time elapsed is the work that you provide. The work is measured in watts, and watts is 1 joule per second. 1 kilowatt is 10⁻³ watts, and kilowatts per hour is not power. Kilowatts, P, kilowatts, power. By time, this is work. And normally your invoice of energy is in joules and is in kilowatts per hour. And the energy that the bill of electricity comes to you is not about power, it's about joules. It's kilowatts per hour, it will be joules, it will be energy, it will be work, it will not be. So the other equation that you have to see is, because the power is the work delivery divided by the time elapsed, the work delivery is the force by the displacement, but the displacement divided by the delta t is the velocity, so the power is also Fx by Vx. If you do it in the s direction, let's say in this s direction, the work is the force in the s direction by the displacement in the s direction, let's say, divided by the time, so the work will be Fs by delta Vs. Let's see, The only thing that remains is that 1 kilocalorie is a unit of energy, and it corresponds to 4,200 joules. So normally you need 2,000 kilocalories per day. That means that you need an amount of energy per day, kilocalories per day, to survive. So to survive, you need 2,000 kilocalories per day. So that means that you need 2,000 by 4,200 joules. So this multiplication will be joules. So you need this amount of joules per day. So you need 84,000 of joules per day to survive. So you need per second, because one day is 24 hours, 1 hour is 60 minutes, 1 minute is 60 seconds, you need around your power per day, the energy that you consume, delivered to you, divided by the time that you delayed into consume this energy, is 84,000 joules divided by all this time. This is approximately 100 watts. So the power where you are working, the power that you are surviving every day is 100 watts, or 100 joules per second. So you are consuming 100 joules every second. Wow. Okay. That's all. I hope you like this video.